Welcome! In this video, we will talk about the specifics of the PMBM update. And that includes the Poisson point process intensity for the undetected objects and the detected, misdetected, and new Bernoullis. We're going to look into what we can call the building blocks of the Poisson Multi-Bernoulli Mixture update. So in the PMBM model, we have undetected objects and detected objects. And any object that previously has never been detected will either remain undetected or will be detected for the first time. So for the previously detected objects, they are either misdetected in this time step or detected again. And this gives us 5 so-called building blocks of the Poisson Multi-Bernoulli Mixture update. The first is the update of the Poisson point process intensity for the undetected objects that remain undetected. The second is the update of a potential new object. In other words, an object detected for the first time. And this will give us a new Bernoulli. Then we have the update of a Bernoulli with an associated measurement. This is similar to what we had in the MBM filter. And there is also the misdetection update for a Bernoulli. And again, this is similar to the MBM filter. And lastly, we have the posterior log weights. Let's begin with the undetected objects that are misdetected again. The posterior Poisson point process intensity for objects that remain undetected is equal to the probability of misdetection 1 minus the probability of detection times the prior intensity. So what this equation means is that the posterior intensity is going to be lower in areas where the probability of misdetection is low because it's unlikely that an object was not detected there. And similarly, the posterior intensity is going to be higher in areas where the probability of misdetection is high because it's likely that an object was not detected there. When we have a mixture representation of the intensity, the posterior intensity is the sum over the prior components. And for each component, we have the prior weight, the probability of misdetection, and the prior component density. We can express this as the weight times the component-specific probability of misdetection, PMD, and the probability of misdetection times the prior density normalized by PMD, where PMD is defined as the integral of the probability of misdetection and the component density. So from this, we can identify what the posterior weight and the posterior component density are. Here we have an example prior undetected intensity with 5 Gaussian components. In this example, the probability of detection is constant 0.75, and this gives us the posterior intensity shown here. We can see in the figure that for all values of the state x, the posterior intensity is lower than the prior intensity. The probability of misdetection is 1 minus 0.75, so equal to 0.25. And we multiply each prior weight by 0.25, and that gives us the posterior weight. The Gaussian components are unaffected when the probability of detection is constant. So this illustrates how we handle the Poisson point process intensity for objects that remain undetected. Next, we have objects that are detected for the first time. If the association psi j is equal to 0, then measurement zj is either clutter or from a previously undetected object. For the previously undetected objects, our prior is of course the Poisson point process model for the undetected objects. So in the base update, this is the prior for this association. We get a new Bernoulli component in the posterior multi-Bernoulli that has a probability of existence that is equal to an intensity function rho divided by the clutter intensity lambda c plus rho, where rho is defined as the integral of the probability of detection, the measurement model g, and the prior undetected intensity lambda u. So as we can see, rho is a function of the measurement. So it will have a different value for different measurements, and thus the probability of existence of the new Bernoulli will be different depending on the value of the associated measurement Zj. the state density of the new Bernoulli is equal to the probability of detection times the measurement model G and the prior intensity, normalized by dividing with rho. So as you can see, the prior for the state density is the undetected intensity. And note that the base posterior is a density, even though the prior is an intensity and not a density. For the posterior probability of existence, conditioned on the association, we have that it is the relative intensity of the measurement being a detection from a previously undetected object and the intensity of the measurement being clutter. And lastly, we have the predicted log likelihood, which we need to compute the log weights of the posterior multi-Bernoulli. This is equal to the logarithm of the sum of the clutter intensity and the intensity rho. So we're going to illustrate both the probability of existence and the state density in some examples. But first, we can discuss the probability of existence a little. Earlier, when we presented the multi-Bernoulli mixture filter, we had that conditioned on the data association, the Bernoulli probability of existence was equal to 1. And the reason for that was that we cannot associate to an object that does not exist. So if that is the case, how can we now all of a sudden have a new Bernoulli with an associated measurement and a probability of existence that is less than 1? And the answer to this is that the new Bernoulli represents two possibilities. First, we have that the detection was from clutter, in which case we do not have a new object, and the likelihood of this is equal to the clutter intensity lambda c. Second, we have that the detection was from a new object, and the likelihood of this is equal to the intensity rho. And these two possibilities are represented compactly by a single new Bernoulli, whose probability of existence is equal to the relative likelihood, the relative intensity of rho and lambda c. Now, we could represent this as two hypotheses, one in which we do not have a new object, and one in which we have a new object with probability 1. However, doing so is inefficient in terms of computations. It is better to have a single Bernoulli with probability of existence between 0 and 1. So let's illustrate this probability of existence with a one-dimensional example. The prior undetected intensity is a Gaussian mixture with 5 components. The probability of detection is 0.9, and the measurement model is Gaussian with mean equal to the object state x and covariance r. The likelihood rho is then a Gaussian mixture with 5 components, where the prior weight is multiplied by the probability of detection, and each Gaussian has mean equal to the predicted measurement, which is equal to the prior mean in this measurement model. And the covariance is the innovation covariance, which is the prior covariance plus the noise covariance r in this example. For the clutter, we assume a standard model, which is that the clutter is uniform. And this gives us a probability of existence for the new Bernoulli that is equal to the sum of Gaussians divided by the sum of the clutter intensity and the sum of Gaussians. So here we see the prior undetected intensity lambda u. In red, we now have the intensity rho, which is lower due to the probability of detection and has larger variance due to the measurement noise. If we compare the intensity rho with the clutter intensity, we see that for some values of the measurement Z, the clutter intensity is larger, and for other values of the measurement, rho is larger. We can expect a higher probability of existence where rho is larger, for example, in the middle, and a lower probability of existence where the clutter intensity is larger, for example, on the left side. So in this figure, we show the intensity rho as a solid blue line, the clutter intensity as a dashed blue line, and the probability of existence as a solid red line. And note that we are using two y-axes. On the left, we have the axis for rho and lambda c, and on the right, we have the axis for the probability of existence. Just like we expected, the probability of existence is larger where rho is higher than the clutter intensity, and it's smaller where rho is lower than the clutter intensity. If the measurement is equal to 0, for example, the probability of existence is larger than 0.8. But if the measurement is equal to minus 25, the probability of existence is almost 0. Let's take another example, where we instead focus on the state density of the new Bernoulli. This time we will use a two-dimensional example, where the state consists of position and velocity. The undetected intensity is again a Gaussian mixture, the probability of detection is 0.9, and the measurement model is linear and Gaussian, where the measurement model H picks out the position and we have a noise covariance R. The state density of the new Bernoulli is a Gaussian mixture, with one component for each Gaussian component in the prior intensity mixture. For each posterior component, the mean and the covariance are given by the Kalman update. The weight is given by the prior weight times the probability of detection times the predicted likelihood, which is Gaussian, with mean equal to the predicted measurement and covariance equal to the innovation covariance, and then we normalize by dividing by the sum over all components. Next, pruning and merging is typically performed on this mixture density to reduce the number of mixture components. In a PMBM filter, it's actually possible to have Bernoulli state densities that are mixture densities. However, often we reduce to a single Gaussian. So here we have a prior intensity where we show the different Gaussian components. In total, there are 16 components spread over 4 locations. The weights of the different components are illustrated by changing the color. Orange is higher weight, gray is lower weight. We also have a single measurement in the bottom right corner, close to the 4 Gaussians that are located there. In the posterior state density, we get 1 Gaussian for each Gaussian in the prior intensity. So in this example, we get 16 Gaussians. And if we zoom in, we can see a bit better in this figure. So here we have illustrated the posterior Gaussian mixture by drawing the covariance ellipse as well as the velocity vector for each Gaussian. Again, the different colors illustrate the weights. Orange is higher weight and gray is lower weight. If we prune this Gaussian mixture with a pruning threshold equal to 10 to the power of -4, then 4 components shown here remain. And note that we have zoomed in further in this image. Now actually, these 4 posterior components are all from the 4 prior intensity components that were located in the lower right corner. Lastly, we can merge these 4 Gaussians into a single Gaussian, which is shown in blue here. And if we zoom out, we can illustrate the posterior Gaussian together with the prior intensity and the measurement. In this example, the measurement was quite close to 4 of the 16 prior components. This does simplify a little. However, we can handle any measurement in the same way. So here we have a measurement that is not close to any of the 4 positions where the prior Gaussians are located. Nonetheless, if we compute the posterior mixture and do pruning and merging, we get a single posterior Gaussian that is a reasonable posterior density. However, as we saw earlier, the probability of existence for these 2 examples would be quite different. So this shows us how we handle undetected objects and objects detected for the first time. We also have the objects that have been detected before. For a prior multi-Bernoulli hypothesis H, if a measurement association psi j is equal to I, then the posterior parameter for the ith Bernoulli are given here. And this is the same as we had in the multi-Bernoulli mixture filter for a Bernoulli that is associated to a detection. And for a prior hypothesis H, if there is a Bernoulli index I for which there does not exist any measurement index j such that psi j is equal to I, then the posterior parameters are given here. And again, this is the same as we had in the multi-Bernoulli mixture filter for a Bernoulli that is associated to a misdetection. And lastly, we have the predicted log likelihood, which we need to compute the log weights of the posterior multi-Bernoullis. And again, these are the same as we had in the multi-Bernoulli mixture filter. So we can note the similarity to the Bernoulli update in the multi-Bernoulli mixture filter. However, we will have some differences in how we compute the log weights of the posterior multi-Bernoullis, and also in how we define the cost matrix that is used to solve the optimal assignment problem. For a prior multi-Bernoulli H and a data association psi, the non-normalized posterior log weight L tilde is equal to the prior log weight plus the sum of log likelihoods of Bernoullis that are misdetected plus the sum of log likelihoods for measurements that are associated to a previously detected object plus the sum of log likelihoods for measurements that are associated to either clutter or a potential new object. Just like we did in the MBM filter, we can rewrite this by adding 0. And doing so, we get the prior log weight plus the sum of misdetection log likelihoods for all Bernoullis plus the sum of the difference between the association log likelihood and misdetection log likelihood for all measurements associated to a Bernoulli, plus the sum of log likelihoods for measurements associated to clutter or a new object. So the sum of misdetection log likelihoods is independent of the measurement association psi. So we can write this as the prior log weight plus a sum of log likelihoods L tilde for each measurement, where L tilde is defined as shown here. Note that this allows us to express the optimal assignment cost matrix using the L tildes for each Bernoulli H. However, to compute the posterior log weight, we typically need the sum of misdetection log likelihoods, because this might not be equal for all prior hypotheses. So now that we have the 5 building blocks of the Poisson Multi-Bernoulli Mixture update, we can illustrate the update with an example. In this example, we have a prior Poisson Multi-Bernoulli mixture with 2 multi-Bernoullis, each with 2 Bernoullis with Gaussian state densities, and we have an undetected Poisson point process intensity with a single Gaussian. The probability of detection is 0.75. The measurement model is Gaussian with noise covariance 9 times an identity matrix, and the clutter intensity is 4 times 10 to the power of minus 4 in the surveillance area and 0 outside. And in this example, we have just a single measurement. So for each prior multi-Bernoulli, we will have 3 data associations, and thus we get a posterior multi-Bernoulli mixture in the posterior Poisson Multi-Bernoulli mixture density that has 6 multi-Bernoullis. Here we have the prior PMBM with 2 MBs with weights 0.3 and 0.7. The prior Bernoullis are illustrated as blue ellipses with probabilities of existence written next to the means. The prior undetected Poisson point process intensity has a single Gaussian with weight 0.1, illustrated in orange. And lastly, we have a single measurement. So for each prior multi-Bernoulli, we have 3 possible data associations. First, we have that the measurement is associated to clutter or a potential new object, in which case we get a new Bernoulli. In this example, it has probability of existence 0.58. We can also see that the misdetected Bernoullis, in both posterior multi-Bernoullis, the 2 misdetected Bernoullis have lower probabilities of existence, and the weight of the undetected Gaussian is lower. So note that in both of the posterior multi-Bernoullis, the new Bernoulli is actually identical, even though the 2 prior multi-Bernoullis are different. And the reason for this is that in both posterior multi-Bernoullis, the prior for the new Bernoulli is the same, and that is the undetected intensity. Second, we have an association of the measurement to one of the prior Bernoullis, in these 2 illustrations to the prior drawn on the left. And lastly, we have the association to the other Bernoulli, so in these illustrations, the prior drawn on the right. And we see that we now have a different number of Bernoullis in the posterior multi-Bernoullis. In 2 of them, we have 3 Bernoullis, and in 2 of them, we have only 2 Bernoullis. And the reason for this is that the initiation of new Bernoullis is measurement-driven. Instead of adding Bernoullis to each multi-Bernoulli in the prediction step, we only initiate a new Bernoulli when a measurement is not associated to a previously detected Bernoulli. In the PMBM filter, we handle the data association analogously to how it's handled in tracking a known number of objects and in the MBM filter. Gating is used to remove highly unlikely associations and to group the measurements and the Bernoullis. A cost matrix with negative log likelihoods is formed, and an optimal assignment method is used to find the M associations. For example, we can use the optimal Mertis algorithm or the suboptimal but efficient Gibbs sampling. And all other associations are truncated. So after finishing this video, you can go back and review this material if you feel uncertain about it. The cost matrix for the optimal assignment problem can have the following structure, which is similar to what we have seen before, although here we are computing an assignment from measurements to objects, and earlier we did it from objects to measurements. We have a left submatrix for the associations between measurements and previously detected objects, and a right submatrix for associations between measurements and previously undetected objects. The log likelihoods are defined as shown below. We have the log likelihood of either clutter or new object, and then we have the relative log likelihood of detection and misdetection. That was the Poisson Multi-Bernoulli Mixture update. We mention it again when we talk about track-oriented implementation. Next up is PMBM density reduction, which consists of pruning and capping, which we are familiar with from before. But it also includes a new reduction step that is called recycling.